I'm about halfway through grading your first milestone of your project, and I'll have those for you. I'll have those for you for sure tonight. But here's the thing, you guys. There's a common mistake, and I think I might have not been too clear. I might have misled you a little bit. A number of people have actually done more than one finite state machine by virtue of doing parsenum. And I think I remember saying you can copy and paste this previous code that you used. I did not mean, actually let me explain it this way. This figure 7.53, that's the only finite state machine that should be in your project. Okay? And a number of you used more than just 3 loops. You used the loop to do this, but then you used parsenum that had its own finite state machine that had its own loop in it. And that's incorrect. So when you get your homeworks back, you know, with them marked up, make sure that you follow the guidelines for your next submission. In fact, by the way, you guys, anytime I mention something to change in your code, that's not optional. You need to go back and fix it for the next milestone, all right? So don't just, you know, say, okay, well, he said do this, but you don't really have to do it. You really need to, any comments that I make about your code about changing things or changing style or whatever, make sure you do that. Okay, make sure you incorporate that for your next milestone. So anyway, that's one thing I just wanted to mention for the record. But anyway, you'll see the comments whenever I return your programs tonight. Now, also, we have a homework assignment that's due today, but we're going to postpone that till tomorrow because, and a number of people came in and asked me about it, and I said, well, we'll just talk about it in class today. But our goal today is to explain how to do your next homework assignment, which is going to be the last written assignment in this course. From now on, after this assignment, everything else will be code. So that's our goal for today, is to understand how to do that homework assignment. Now, and in preparation for that, figure 7.27 is a diagram of the stages of translation for a typical translator. And remember, there are 3 stages. There's the lexical analyzer, which is based on this deterministic finite state machine that you just did. And the second phase is going to be the parser. And in most HOL6 languages, the parser is based on a grammar. All right? And then the third phase is code generation. Now, actually, I didn't mention this before, but it is on the figure. The first 2 phases together, the lexical analyzer and the parser, that is called syntax. What you're doing is you're analyzing the syntax of the program. And the code generation is what's called the semantics, the meaning behind the syntax. Now, this is the way it is for an HOL6 language. However, what we're going to illustrate now is that for our assembler, the parser is not based on a grammar. PEP9 assembler. Okay, so unlike in figure 7.27, the parser is based on another finite state machine. Parser is based on a finite state machine instead of a grammar. Now, do you remember when we were studying by the way, what are the 3 ways to specify the syntax of a sentence of a language? Remember those? Finite state machine, grammars, and regular expressions. And do you remember which one is more powerful, a finite state machine or a grammar? Yeah, a grammar is more powerful. But now the thing of it is that our PEP9 assembly language does not need to be, it's so simple that it doesn't need a grammar in order to parse it. That's why we're doing it with a finite state machine, is because we don't need to. And the reason we don't need to is because nowhere in our language do we have nested parentheses? That's the key feature. That's one of the key features that you need a grammar for in order to parse a sentence in a language. If the language, if you have the ability to nest, to have arbitrary nestings of parentheses, you can't do that with a finite state machine. But see, we don't have that in our language, so therefore we can use a finite state machine for the parsing phase, for the parser, for the second one. Is everybody clear on this? But you need to be aware that in programming languages, they're based on grammars, and it's a different story for HOL6 languages. But for many assembly languages, we don't need that complexity. Here's how we're going to proceed for the next stage of the next two stages for the rest of your project. Up until now, we've been doing, I've been showing you example code, and for the next two phases of your project, I have set up a language translator, and just so that it would be not giving away too much detail, this language translator doesn't have anything to do with our PEP9 assembly language. So this language translator that we're going to inspect and we're going to study, we are going to learn these parsing techniques from this language translator, but it's for a fictitious little toy language that I just designed in order to teach the concepts of how this works. And so your homework assignment that was due today but is now due tomorrow, it's to design a finite state machine for the parser. Are you with me? So normally we said parsers are based on grammars, but this time it's based on a finite state machine. I'm not giving you the finite state machine for the parser. You have to write it. You have to design it. And then you will and then your code will implement that. So what we want to do now is we want to look at this little sample language translator and see how it works, and then that will be a model for you. We will take a look at a model finite state machine for this translator, and then that's what you will use. That's how you will go about designing the finite state machine for the PEP9 assembler. Is everybody clear on where we're heading here? Are we good? Now, what I want to do, I have the output in these slides coming up, but I think before we take a look at the slides in detail, I just want to run a quick demo. Okay, so here is going to be our demo. Now, the program that I want to run here is figure 738, so we'll just click on this and do a run, and we'll show you what happens. So now look up here, we have our input field like we had before, and this time the button says translate. So now here before your very eyes, we will see a translation happen. Now watch this. What I have is, I have already pre-written some code here. So this code that is shown here in this text editor, I'm going to just copy it. And you see what the language is like. It's like set, parentheses, time 15, and we'll talk about this in a minute in the slides. And we have uppercase and lowercase for these mnemonics, and there's a stop and there's an end. So let's just copy that, and let's go back to our Java app and paste that in. And let's take a look at our, so here the output is going to appear here. So let's go. Now watch what happens when we do translate. Now here are you ready for this? Drum roll. Boom. Now look at what this program did. What it did is we put the source code in here, and what the translator does is it has a little section called object code. And this is the object code for this little toy language. So what it did is it translated from this language to this language. And not only that, after it did the object code, it did a what? program listing. Now your job for the second milestone of your project is going to be to do this program listing without the object code, because that'll be the last phase. So are you with me on that? So what you will do is when your next phase of your project, when you click translate, the program listing should come out. Not the object code, but just the program listing, because we're not, generating the object code is the last phase of the project. So you see how that, and look at what it did to the input when it, in the program listing. You see when it made the capitalization all uniform, it spaced it all out real nice. You know, all these extra spaces were all eaten up and taken care of, and it came out in a nice little program listing like that. So your job is going to be to have the program listing come out exactly the way the program listing comes out on the desktop app. So you should model it after that. You should model your output like that. So that's an example of when we have, this is an example of what happens when we have valid code, but now watch this. Let's go back to our text editor, and here's a bunch of code that has errors in it. We'll talk about the errors in a minute on the slides later, but let's copy this and go, oops, went the wrong way. Go to our app and let's paste it in here, because look, the user of your translator might have errors in their code. So look what happens when they do. Actually, let's get a few more lines here. Okay, so watch this. Boom. Now look what it says here. What does it say up there? 9 errors were detected. Program listing. And now look at how descriptive these errors are. So you're going to have to code these error messages for your user. You see? So what this says is, you know, error, second argument, not an identifier integer, error, comma expected after first argument, error, blah, 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 blah. And then error missing end sentinel. Notice it didn't have the end up there. So anyway, that's the kind. So what we will do is in the chapter 7 of the text, we can study this code and use it as the principles there as a model for how to do the second stage of your assembler. Is everybody good? All right, so in the demo. Okay, so that was our demo. Now what let's do is let's take a look at that in a little bit more detail, and with the goal of showing you what you need to do in order to get your next homework assignment done. So here in figure 7.37 is on this slide, it's the same input and output as what we just saw on the screen, but now let's take a look at it in a little bit more detail. Okay, first of all, I just made up this input language, you know, where it says input there. And so what does it look like the features of the language are? The first, on each line, what does each line start with? Some sort of a function, yeah, it looks kind of like a function. And that function is kind of like, they all start with a letter, and, you know, so they're kind of like identifiers, all right? So, and what are some of the functions? Set, mul, div, stop, end. And look, some of them, how many arguments does set take? Yeah, it takes 2. And how many arguments does, I guess, wait a minute, I guess they all take 2, don't they? Oh, well, yeah, except for stop, which doesn't take any. And we'll see a little bit later on, I should have a listing. Some of them, or you can read it in the book, some of them only take 1. Like if there's a negate function that if you do like this, if you say neg position, then this only takes 1 argument. And if you do this, what do you suppose the code that gets generated? Can you tell by looking at that code? Can you surmise what this would do? What code would get generated for this? Position would get what? Yeah. So the code that would be generated would be this. All right. So some of the functions have 2 arguments, some have 1 argument, some have 0 arguments. Now this is kind of similar, isn't it? Because to a feature of PEP9 assembly language, because what kind of instructions do we have in PEP9 assembler? Yeah, we have unary and non-unary. So some have and some don't. So you see how, so you use these techniques for how to handle this situation, transfer them over to how to handle that situation in PEP9 assembler. Everybody see the procedure here, what we're doing? So take a look at what, when it says set time, comma 15, the object code is what? Time and then left arrow 15, and then set XL3. And so T squared, and so that left arrow is like gets, you know, that's like in R, the R programming language. That's how you do assignment in R. So does everybody understand the format, the rules for writing a valid input line, and then what the output is, the object code? Does everybody see how that works? I haven't set up a formal grammar with a finite, you know, but you can just, it's simple enough to where I think you can see it, right? And then notice then again that the program listing is, has everything all in a canonical format. Notice how the div in the input is lowercase d, uppercase I, uppercase v, but then it's all the proper. And now can you recognize here that this is going to be the function of the maps, the Java map, right? Because in the Java map, that's what we did. We saw how to do the planets, uppercase, lowercase, whatever, and then we did the maps for the, so that's what you'll do for your, so everybody see how to, how you will use this. I mean, when we see how this is done, how you'll do it. And then here on the next slide, next part of the slide in figure 7.57 is some erroneous output. Now let's take a look at each one of these errors. So if you say, with the input line, set alpha, comma, comma, 1, 2, 3, what is the error message? Error. Second argument, what? Yeah, not an identifier or an integer. That's because it had the comma, and then it was looking for another identifier, but it was a comma. Are you with me? And then what about the next one? Set alpha. Well, yeah, it requires 2 arguments. What did it get after? What was it expecting after the alpha? But what did it get? A right paren. It got a right paren. So that generated comma expected after first argument. Next one, sit. What did the user do? Misspelled set. So what's the line must begin with a function identifier. And then how about the next one? Set comma. The message left parentheses expected after a function. It got a comma instead. And then what about mul? No right paren. Okay, does everybody see how that? And then let's see, what was the next one? Set, oh, but that's 1, 2, 3. So what about that 1, 2, 3? You can set alpha to 1, 2, 3, but you can't set 1, 2, 3 to alpha, right? Because it's a constant. So that's an error in this little toy language. Does everybody see how where that error came about? And then, and neg. Neg is the one that I showed here. It only expects 1 argument. Okay, but what this said neg alpha beta. So it expected a right parentheses after that first argument. And what about that set alpha comma 1, 2, 3, but with x? It is illegal trailing character. And now if your user omits the dot end, you need the dot end for the sentinel for the assembler. So this corresponds to that. You see, a valid program in this toy language the last statement has to be end for the sentinel for the assembler, for this little assembler. All right, now does everybody get the language, what it does? Now what we want to do is we want to take a look at some of the principles about how it works. But what I want to focus on now is figure 7.41. Now, figure 7.41 is a UML class diagram for the tokens in this language. Now, you guys have already done your tokenizer, So these tokens correspond directly to the tokens that you have already written your tokenizer for, right? But these are the tokens that this little toy language uses. So let's just take a look at them. So first of all, we have an abstract token, and then we have a T identifier, a T integer, a T comma, a T left paren, a T right paren, a T empty, and a T invalid. Now, are those all, do you see where those all came from? Let's go back. Let's go back to this figure 7.37, this valid, with this valid input. So can you tell me what, let's just take a look at that first piece of code. Set, paren, time, comma, 15, close paren. Set, paren, time, comma, 15 paren. Now, with this, so let's keep this in mind. Let's keep this code in line. And in figure 7.41, with these, so what do you think the stream of tokens is going to be from the lexical analyzer when the program parsed this line? Yeah, first it's going to be an identifier, so T, and that will be for this, right? So that'd be T identity, and then what will it be? It'll be T left paren. So this it will detect as a token, a T left paren. Are you with me? So this will be a T left paren, and then what will it do? T identifier. And then what will it do? Obviously. This is so trivial. But anyway. T comma, and now what? T integer. It will detect this as an integer, so it'll be a T integer. And then what will it detect? T right paren. But we're not done yet, sports fans, because what then will it detect? Yeah, it will detect T empty at the end of the line. Are you with me? So look, you guys, what the input to the lexical analyzer is a stream of what? Not the lexical analyzer. The input to the lexical analyzer is a stream of what? Terminal characters. The output of the lexical analyzer is a what? Stream of tokens, which is then the what? The input to the parser. Now, do you see that this is the stream of tokens that is emitted by the tokenizer that then goes into the parser? Is everybody clear on that? That's what this is. All right? Now, we said that our parser is our parser going to be based on a grammar or on a finite state machine? It's going to be based on a finite state machine. So I ask you, sports fans, that finite state machine is going to have a transition on each what? On each token. Now, does everybody see what we're saying? That finite state machine is going to have a transition on each token. So here's what we've got, you guys. We have the finite state machine for the lexical analyzer. Terminal characters are coming into that, and what's coming out? Tokens, and then we're going to have a what? Another finite state machine for the what? For the parser, and what's going to be coming into that? Tokens. And what's going to be coming out of that? Some intermediate code. That's the output of the parsers, the intermediate, the parsed intermediate code. There's going to be a table, a code table. Are you with me? So now what let's do is let's take a look at that parser, all right? And that parser for this little toy language. And that parser for this little toy language is going to have a transition on these tokens. All right, so here it is. Okay, so now in figure 7.46 now in the book, in the text, this is the finite state machine for this little toy language, right? And what your job for tomorrow is to write the equivalent finite state machine for your parser for your assembler, all right? So let's take a look at this finite state machine for this, all right? So now look, you see in the upper left-hand corner, it's PS start. Now what does PS stand for? That's the, you know, we had, LS was the lexical analyzer state, PS is the parser state, okay? So that's our little convention. And so here we are in the upper left-hand corner, PS start. Now look, in this particular example that we did, what gets emitted from the lexical analyzer? First, a what? So if we start in PS start here in figure 7.46, where does T identifier take us? Well, now, wait a minute. It looks like, holy cow, is this non-deterministic? It looks like we could either go to the right or we could go down.
Well, but it depends on which identifier.
Yeah, see, and you're going to have to do this too. This is a deterministic finite state machine, but I have this little, it's footnoted. Do you see? The T identifier on the top has footnote 1. Only the identifiers stop and end go that way, right? But this T identifier is going to be a what? It's going to be a set. Is everybody clear? This T identifier is going to be a set. So that set, so because it's not a stop or an end, then we go down. So now what state are we in? After we scan, after we make a transition on T identifier, what state are we in? PS function. Then what happens here? T left, well, what does it say there? T left paren will take us down to where? What state? PS open. And then what will happen? This T identifier will take us where? To PS first operand. And now what's the next thing? A comma. So a comma will take us where? Down to PS comma. But look, that's only for what? Only for mnemonics. Can you read that? Only for mnemonics set, add, sub, mul, and div, because those are the ones that require how many arguments? 2 arguments. So do you see in your finite state machine, you're going to have to distinguish between unary and non-unary instructions. Yes, that's a really good point. When you draw up your finite state machine, you note it, you use footnotes like this the same way. Mm-hmm. That's do it that way. All right. So now where are we? After this T comma, we are in what state? PS comma. And now look, what's the next thing that we scanned? A T integer. But now look, so we can go on either a T identifier or a T integer to what state? PS second operand. And then this, and then now a scan on what? Right paren will take us to where? PS non-unary 2. And then what? TMT will take us to what? PS finish. Now, you guys, do you see what your job is and how to do it? Because here's what you should do, and I urge you to do it this way. Actually, maybe we should just do this right now. Let's take a look at figure 7.53. And let's enumerate all of the tokens that we have, that our lexical analyzer will detect. Are you with me? If you terminate on the start state, what have you detected? No, which token? The empty token, right? So what are our tokens? Our tokens are empty. Let's just say T empty. And then if we wind up in ls int 1, what have we detected? 0, which is a what? Which is what kind of a? It's an integer. So we have a T integer. And then if we wind up in ls int 2, what have we detected? Integers, same thing. If we wind up in ls hex 2, what have we detected? T hex. If we wind up in ls ident, what have we detected? T identifier. If we end up in ls.2, what have we detected? A dot command. I mean, whatever you call these, I mean. And then if we wind up in ls.addr2, what have we detected? T addressing mode. All right, so look, there's 1, 2, 3, 4, 5, 6. Your job is to write the finite state machine that will recognize a valid PEP9 assembly language statement. Are you with me? And each transition on that is going to be on one of these what? One of these tokens. So now what let's do is let's take a look, let's review what some of those assembly language statements can look like. So check this out, you guys. Suppose, oh, and by the way, fortunately for you, we're not going to implement symbol tables. So we don't need to have, you don't need to do a symbol colon, you know. By the way, I challenge you to do that. I had a student last year who did the whole thing with the symbol table. Worked. Yeah, so I challenge you, if you think you're a good coder, you're interested, to include, you have to go back and modify the lexical analyzer to be able to detect a colon after an identifier as a symbol, and then you're going to have, and then it's easy to use a Java map to do the symbol table and to look it up. But it's a little bit more of a challenge. But anyway, I digressed. So let's do a few sample assembly language, PEP9 assembly language statements. So suppose we have this. Store word accumulator 0x0019, comma, D. This is certainly a valid PEP9 assembly language statement, right? So let's just think of what your parser will have to do, what your parser will do. It will detect this as a what? As an identifier. And then what it will do is it will look up in the Java map to see if it's in there. Remember we had contains? And if it's in the list of the ones that are contained, that's how you will detect that it's it's a valid identifier, a valid mnemonic. All right? So that will be a what? This will be a, so there should be, you know, from the start state, there should be a transition on an identifier to another state, and then what? And then what token will be returned by this one? No, well, which one? This will be a T hex. So then there should be a transition from that on T hex, on that one to T hex, and then what will get? Now, I don't think we have a comma as a. Yeah, we don't have a. We included. We merged the what? The comma and the next one as a what? Yeah. So our token here is an addressing mode. So then there should be a transition from that state to an addressing mode, right? Are you with me? And then there should be. Now let's take a look. Let's take a look at one feature here in Figure 7.46. And then the only way we can get to the end, a valid end, is if what? Our finish, we have empty. Notice that our PS finish only has transitions to there on the empty token. So then the empty token, would take you to finish. Now, okay, now does everybody see how to do your homework for tomorrow now? It's to knowing what a valid assembly language statement is, and with this list of tokens on each transition, draw the finite state machine on a piece of paper, hand it in class tomorrow. And so you just knowing what a valid assembly language statement looks like. The other kind of statement is what? Well, what's another kind of statement? Yeah, you could have dot block, yeah, or a hex, like dot block 2, but no addressing mode. Are you with me? And I think, you know, there are unary ones and there are non-unary ones. Okay, now, the way our lexical analyzer works is the comma and we took this as an identifier. The comma and the identifier is what gave us the addressing mode. And so because here, let's take a look. On figure 7.53, you see in our language, we don't have comma as a separate token. We combined it with just a letter, you know, a transition from ls address to itself on a letter. Are you with me? As an addressing mode. And so what will happen if you get an addressing mode? If you get a T addressing mode, here again, how will you know if it's a valid addressing mode? You'll do a what? You'll use a what? Yeah, you'll use a Java map. So you'll have a map for the comment for the valid addressing modes. And then whatever addressing mode you get from that returned token, you'll look it up, and if it's an I or a D or whatever, it'll be valid. If it's not, it won't. It's not valid. Yeah.
So when doing it?
Yeah. Did we do? I don't think we did single quotes.
Okay. Yes, that was perfect. So
Yeah.
it would just be like this situation.
Now, is everybody clear on what it is that you have to do? So your figure should look something like this figure 7.46, except that the transitions are on these, and it should be appropriate to parsing a valid PEP9 assembly language statement. Now, is everybody clear on how to do that homework assignment? Like I said, this is your last written assignment. From now on, it's all coding. Yeah. Okay, now hold on. That's a good question. Now let me. The question is about. Let me answer that question. The question is about spaces between tokens. Now check this out. In figure 7.53, notice that in the start state, once you finish scanning, identifying one token, there could be any number of spaces after that token. Because when you start over with this finite state machine, what will you do? What will happen with all those spaces? You'll be making a transition to the start state on those spaces, so they will get consumed that way. So that's all built in. Is that slick? You don't have to do, you see what I'm saying? You see what I'm saying? And not only that, that works for leading spaces, that works for trailing spaces at the end of a line. All those cases are all covered by this good design of a finite state machine. And only 3 loops, one per line, one loop per line, 1 loop per token, and in the lexical analyzer, 1 loop per input character. Yeah.
But it's not making, the only time it makes an input.
Correct. But when you run out of space, like if furthermore, the line may or may not have spaces on it.
Right.
Either way, if there are spaces, it will consume it. When it gets to the new line, it'll be empty. Okay, ask that question again. You're at ls start, and we're transitioning to ls start on some spaces. That's if we have some leading spaces in front of the next token.
So it's
Well, first of all, there are 2 different types. A space is a terminal character in the alphabet, and empty token is a token. So you detect an empty token when you get at the end of a line. Because where you are is, because you are going back to the beginning and scanning for the next token. But if there are no characters other than spaces, you will transition to the start state on those spaces, and finally when you get to the new line, you will be in the start state and you will be at the end of the line and you will detect the empty token. Now, that was a good question. This is always a little confusing. Are we good with that? Yeah. Does everybody see how this works? Okay. All right. We're a few minutes early, but I think we can call it quits if there's no more questions. Okay, so see you tomorrow with your finite state machines.